So, electromagnetic field and its quantization. So, in order to discuss this topic, we have to start from classical electromagnetic field. Now, classical theory of electromagnetism combines together three fundamental and observable phenomena: electricity, magnetism, and light. And photons are presented in terms of electromagnetic waves. And as you know, these waves propagate in vacuum with the speed of light. What is important is that the theory of electromagnetism is relativistic invariant from the very beginning. And if people would think about this maybe at a more deep level, namely under which transformations Maxwell equations are invariant, I think the theory of relativity, special relativity, could be discovered earlier than it has been done by Einstein, because Maxwell equations has been known already for quite some time. And if you think about them, then they are invariant with respect to Lorentz transformations. So it means that relativism is built in into the Maxwell equations. And if you would analyze it closely, you would find relativistic theory directly from Maxwell equations, from electricity and magnetism as we know them. Now, quantization of electromagnetic field, as we will do later, must reveal the particle nature of light. So electromagnetic waves actually become, in this case, say, flow of photons. Now, the name photon has been coined by chemist Gilbert Lewis, 1926. So it's very natural if we start our discussion from Maxwell equations. And as you know, these are partial differential equations on components of electric and magnetic fields. So electric field I will denote by E, and magnetic field by H. And so Maxwell equations are the following equations. Divergence of H is equal to 0. This is the absence of magnetic charges, signifies the absence of magnetic charges. dH over dt is minus C curl of E. And then divergence of E is equal to 0. I'm writing Maxwell equations without sources. dE over dt is C curl of H. This is how Maxwell equations without sources look like. Now, these equations involve one-dimensional full constant. This is C. It has a dimension of velocity. This is clearly, you can clearly see because H and E has the same dimension. Now, on the left-hand side, you have 1 over time. From this derivative, curl gives 1 over length. And then to compensate the difference, you need velocity, which is length over time. And this is, as we know, is the speed of light. Now, there is a terminology which people adopted. The first two equations, namely this one, this, and this. This is called first pair of Maxwell equations, and correspondingly, this is a second pair. So sometimes also people call this equation here Gauss law. Gauss law, and I will also use this terminology for this equation. It's Gauss law. Now, the first question one would like to answer is how to solve these equations. And the big progress in solving these equations can be made, as you know, by introducing the four potential A mu, which has components. Its time component A0 is denoted by phi, and it's called scalar potential. So scalar potential. And then the three vector denoted by A on X is called vector potential. Scalar potential and vector potential. And, you know, indices of A mu, as usual, are raised and lowered with the help of the Minkowski metric, eta mu. So A mu with low index will have components phi on X minus vector A, like this. Now, the relationship between the electromagnetic potential and the electric and magnetic fields is introduced in the following way. So E is minus gradient of phi minus 1 over C dA over dt, and H is curl of A, curl of vector potential. So magnetic field is fully determined by the vector potential. Now, why this is interesting and important to introduce the electromagnetic potential A mu? That is because of this parameterization of E and H, the first pair of Maxwell equations is automatically solved. It's solved automatically. That is because, you see, if you take, say, H, and H is curl of A, then the divergence of a curl, as you know from vector analysis, is 0. So divergence here applied to a curl automatically gives 0. And also concerning the second equation here, if you substitute here E and H in the form given here, you will see that the that the equation for dH over dt will be automatically satisfied. So introduction, let's write intro of A mu automatically solves first pair of Maxwell equations. So that's why we like the potential. Now, what about the second pair? We can take the expression for E and substitute it into the Gauss law. So Gauss law is divergence of E is equal to 0. So divergence, we apply divergence to minus phi is A0 minus 1 over C dA over dt. And then you have two nablas acting on A0, and this two nablas gives you nothing else as a nabla squared, and nabla squared is the same as the Laplace Laplace operator. So you have minus, but this is equal to 0. Let's write equal to 0. And so minus sign, if you multiply everything by minus, and then I get here Laplacian acting on A0 plus 1 over C d over dt, divergence of A equals to 0. And actually, this equation can be solved for A0 A0 I can write with upper index or with low index, it does not matter. A0 can be solved from this equation. So solution which is valid in the full space, solution can be obtained with the help of the Green's function or the Laplace operator. So A0 then with upper or low, does not matter how to write it, is minus Laplacian in the power -1, so inverse Laplacian, 1 over c d over dt, divergence of A. And we know what is inverse Laplacian. It's a Green's function, which has the following form. So dx, it's an integral, d over dt, 1 over c. 1 over c, let me write it in the denominator, 4 pi c modulus x minus x prime. And then here, divergence of A, like this. Well, it's an local expression because it's a Green's function for the Laplacian, but in any case, A0 becomes it's not an independent field, and we don't need to specify it at initial value, say t is equal to 0, and that already shows that the number of independent component of electromagnetic field is not more than 3, because A0 is solved. Solved through the Gauss law, solved by the Gauss law. And the last thing which we need to solve is this equation, dE over dt is C curl of H. So what this equation gives us? dE over dt is C curl of H. So if you substitute there all our expressions, what we will get? We will get d over dt, gradient of A0, plus 1 over c dA over dt, and on the right hand side we will get minus c curl of A. So vector product of nabla with A and the vector product with nabla again. Yeah, because this is vector product of nabla with A, with vector potential. So there is a formula from vector analysis which says that vector product with another vector is given by gradient of divergence minus Laplacian. And Laplacian I may write as nabla squared acting on A, like this. And so equation which we get is actually, if I open here everything, it's actually rather complicated. Here we have 1 over c squared, 1 over c squared, dA over dt squared, minus nabla squared A, equals to nabla minus 2. Here I substitute A0. This comes from A0. Second derivative c squared dt squared minus 1 acting on nabla multiplied by A, so divergence of A. So pretty complicated expression. That's the last equation we need to solve. What do you think would be a strategy to solve it?
By introducing scalar.
Yeah, you see, scalar potential is already, we have introduced it already. So this is A0. Now A0 I substituted already from the solution we have. It's given by this formula here. And I substituted it already in this formula. So second derivative on time on A comes from here when this dt acts on this dA over dt. So this what gives this term here. And nabla squared A comes from this term. So this is the left-hand side. And the right-hand side, I collected this term nabla A0 d over dt. It is sitting there. It is sitting there, and I substituted explicitly the solution for this A0. So you see, what is pretty complicated is right-hand side, right? What this is expression which is ugly. It is non-local. It contains this nabla minus 2.
No, I mean to say that if we change a mu to a mu prime, a mu plus del mu lambda.
Yes, exactly. Yes, that's what we have to use. Exactly. The interesting point is the following, indeed, that the theory which we consider, as soon as we introduce electromagnetic potential, what's happening? As soon as we introduce an electromagnetic potential, then we notice that our theory shows the so-called gauge symmetry. Gauge symmetry, which consists in a possibility to change our electromagnetic potential by adding to it a gradient of any function, no differentiable function, so chi arbitrary, arbitrary function, arbitrary function of what? Of space-time point, arbitrary function of x, without change of electric and magnetic fields. No, indeed, we can look at this from different point of views. So, for instance, if we just look at E, this is, we know it's a gradient of phi minus 1 over c dA over dt. Phi is A0. And we see that what we get here. So we get gradient of d0 chi. Upon this change, we see that additional terms which we get will be gradient acting on d0 chi minus 1 over c d over dt, and chi here, A will be changed by gradient of chi. And then you see this gradient acting on chi, and then d0, and this is exactly derivative d0 also. This is d0. And therefore these two terms cancel. And there is no change in E. Analogously, if H is curl of A, and if we change A by gradient of chi, then what we have here is curl of a gradient but curl of a gradient is 0, as we know from vector analysis. It's gradient cross gradient. Vector product of a quantity by itself vanishes. And therefore, we know that actual observables, the quantities which we can measure with our devices, are actually E and H. These are observables, physical observables. That's what we can measure. E and H. The field A mu is not really observable, which we can measure, because we see that we have a possibility to change it by adding a gradient of any function without change of E and H. And so there is this freedom. And this is called gauge symmetry because, in a sense, gauge symmetry is attributed to the so-called local symmetries. And local symmetry means that the parameter of symmetry transformations, which in our case is this function chi, this parameter is a function of a space-time point. When it's a function of space-time point, it's a function of x. Such transformations are called local. And so gauge transformations are local transformations when the parameters are not global, but they do depend on a space-time point. Such as symmetries, they are not a subject of the Noether's theorem as we have studied. They do not lead to conserved currents. These gauge symmetries, local symmetries, they simply say that if we adopt the description of electromagnetism with the help of electromagnetic potential, then we meet the redundant degrees of freedom, unphysical degrees of freedom, which are exactly related to the possibility to change the potential by arbitrary function without affecting the observables E and H. Okay, so we have now this gauge symmetry. And in our case, it appears that this gauge symmetry is very, very helpful because by means of this gauge symmetry, by means of the possibility of choosing function chi, what we can do, we can impose on our potential a subsidiary condition. Namely, with one function, we can impose on A one condition. And naturally, looking at this equation, it comes to mind that the good way to impose this condition is to require that our potential should be brought to the form to satisfy an equation. Divergence of A is equal to 0, right? This is a one condition on A, one condition, so one function of A, namely divergence of A, by means of using these gauge transformations, gauge symmetry, we can impose one subsidiary condition, which is called gauge fixing in general. Imposition of such conditions called gauge fixing. And this gauge, this particular gauge for a field A, is called Coulomb or radiation gauge. Either some people call it Coulomb, and some people call it radiation gauge.
So I have a question.
Sure. Go ahead.
Are you sure this gauge condition is a Coulomb gauge, Coulomb gauge, or not a light-con gauge?
No, this is not light cone. This is condition that I can write it using a different mathematical notation. Divergence div of A is equal to 0. It's the same. It's just different notation. So divergence of A is equal to 0. That's subsidiary condition. That's a gauge which we would like to impose. Because, of course, as you see, it's tremendously simplify our equation because of this vanishes. So the whole right-hand side goes away. And the equation now takes a very familiar form of the wave equation. What is written down here, what is left over, is just a wave equation for any component of A. since A is a vector, you see second derivative of A minus nabla squared, which is Laplacian of A, is equal to 0. And this is for every component of A. So A is a 3-component field, 3-component vector. For every component of A, you have just wave equation. The only thing which you have to have in mind is that when you solve it for each component, components are not independent, but they are related by this gauge condition. Divergence of A is equal to 0. And this is the whole system of equations which is left over for you to solve. And this is exactly what describes electromagnetic waves. These are electromagnetic waves. This is where they come from. Wave equation, of course, has solution in terms of waves, so electromagnetic waves. Yeah, this is how this gauge symmetry helps. On the one hand, on the other hand, it tells us that description in terms of electromagnetic potential is a bit redundant in a sense that it brings with itself unphysical degrees of freedom. Too many degrees of freedom sitting in this field A. Now,
sorry, sir. I have another question.
Yeah.
If we choose some gauge condition here, and how can we show its matrix element is independent?
Dependent on what?
Dependent of the choosing gauge.
Yes. So the question is the following: that in principle, you can choose another gauge. There could be many possibilities. The gauge choice can be complete and incomplete. Incomplete means that there are still gauge transformations which you can do without destroying the gauge condition. Such a gauge choice is called incomplete. Complete gauge choice means that there are no gauge transformations left over. So if you do any gauge transformation, then you necessarily destroy the gauge condition. And the idea, of course, I mean, this is something which certainly should be there, is that any two complete gauge choices must be equivalent. In other words, there should be a gauge transformation which relates one gauge choice with another gauge choice. There should be a gauge transformation which brings you from one complete gauge to another complete gauge. The question which you can also ask is why this gauge choice is reachable. Why you can impose on A such a condition? Why this is always possible? The answer is that yes, indeed, you can show that this is always possible to fix this gauge. Let me show this. So suppose you start from suppose you start from some gauge configuration. So from some electromagnetic potential A mu tilde, AI tilde. Then you perform a gauge transformation on it. So you add up di chi. And then you say, well, I want, so you get new AI. And then you say, I want this new AI to satisfy the divergence of A is equal to 0. So you impose the condition di AI, so divergence is equal to 0. So what it means that if I now take di AI tilde minus, so di I raise up di AI, it will give me minus di chi is equal to 0. So this is given. And now the question is, can I find a function chi which satisfies this equation? But you see, di is a Laplacian. So I will get an equation di ai tilde minus Laplacian acting on chi is equal to 0. And this equation you can always solve by means of Green's function. So you say chi is Laplacian minus 1, Green's function, di ai tilde. And this Green's function we know very well. This is minus integral dx di ai tilde divided by 4 pi x minus x prime. So if you give me a potential, arbitrary potential a tilde, then I will find for you a function chi such that making a gauge transformation with this function chi, I will obtain a new potential which satisfy the Coulomb gauge condition. So this means that this is always reachable by means of the gauge transformation. This condition you can always impose. Okay, that is how it works.
Okay.
Now, there is, of course, what we know as a covariant formulation of Maxwell theory. Covariant formulation, covariant in a sense of Lorentz covariance. And this is, of course, proliferate considerations of many things. Also allows to consider action for electromagnetic field, and this is something which we also need to know.
I'm sorry.
Yeah, sure.
Could you please very briefly remind in what sense the operator delta to the power of -1 is inverse to delta? Because the operator delta has non-trivial kernel, so it can't have, strictly speaking, an inverse.
It has an inverse provided you specify type of the Green's function you want. For instance, you can take causal Green's function, or you can take retarded Green's function, or you can take advanced Green's function. The Green's function which I'm writing here is a standard Green's function in the sense that 1 delta acting on 4 pi x minus x prime is equal to minus delta x minus x prime. Okay, have you seen this formula before?
Yes.
Yeah, so this is what I mean by inverse. So this is what I understand as delta minus 1, the Green's function. And you know, if you have how you solve inhomogeneous equation. So if you have inhomogeneous equation, Laplace equation, so Laplace, it's called Poisson if there is a right hand side. So say nabla acting on something, say on chi, for instance, is equal to f. Then solution of this equation is given with the help of the Green's functions. As you know, Green's function allows you to write down a solution as chi given by delta minus 1 f. And this is typically, if in general case, if Green's function you denote by g, this would be g x minus y f on y dy. Right? That is the standard way to solve linear partial differential equation, is to find the corresponding Green's function. And this is exactly what I have done here. I just inverted this delta operator, Laplacian, with the help of the Green's function, and yeah, this is the result. So in this way, you show that the Coulomb gauge is always reachable. And so the equation for vector potential reduces to the standard wave equation, and you have a description in terms of waves. Okay. Now, covariant formulation. I presume you've seen it before, but let's remind a little bit how it works. So you introduce a so-called electromagnetic tensor, F mu. And this tensor is parameterized, its elements, it's a 4x4 matrix, if you wish, and it's parameterized in this way. It's parameterized by components of electric and magnetic fields in this way. So tensor is Q-symmetric. So these are components of electric field. And then magnetic field goes like this, minus Hc, Hy, minus Hx, 0, 0, Hz, minus Hy, Hx, like this. And the tensor with upper indices is obtained by means of raising, say, mu sigma, mu, I don't know, nu rho, f sigma rho, like this. So its components are electric and magnetic fields. And here, how it related to what I said before, so E, my E is Ex, Ey, Ez. And H is Hx, Hy, Hz. Components like this. F menu, where if you analyze how I introduced before, E to be given by minus gradient of A0 minus 1 over C dA over dt, right? And H is curl, okay, let's write it as this, curl of A. Now, if you analyze how it's written in terms of F menu, you see that very nicely, F menu is simply given by d mu A nu minus d nu A mu. That's the same formula as this at these two. So this formula combines this expression of E and H in terms of electromagnetic potential. And so that is concise and covariantly written nicely expression for electromagnetic tensor in terms of the electromagnetic potential. From this formula, you actually immediately see the gauge symmetry. So if your A mu goes to A mu plus gradient, say d mu chi, then you see the change of F mu goes to where? D mu receives A nu, so d nu chi minus d nu, and then A mu receives a contribution d mu chi. And since second derivatives commute for the differentiable function, the result is 0 immediately. Immediately you see the presence of this gauge symmetry and the level of F mu. Now, if you want to express back the components of electric field or magnetic field via F mu, then the corresponding formulas, let me write them down so you see them once at least. They look as follows. Components EI, so EX and EY and AZ, I denote them as EI in general. This is simply F0I. So if you component F0I, well, you see it's 0 and I runs 1, 2, 3. And this is the same as f I0 by the rules of raising and lowering indices, or minus f 0I. And by the way, let me point out explicitly that tensor f mu is q-symmetric, so minus f nu mu. Well, you see it explicitly from the matrix formula. And concerning magnetic field, Fik is minus epsilon IKL IHL, so epsilon tensor is involved. Or if you want component Hi, this is minus 1/2 epsilon IKL FKL. So this is a way how these components can be detected. And this definition of electromagnetic tensor implies so-called Bianchi identities. Bianchi identities. It comes from definition of f mu, and it's written in the following way: d lambda f mu plus then cyclic permutation of indices d nu f lambda mu plus d mu f nu lambda. You see cyclic permutation of indices lambda mu nu, and sum up, you get 0. This is called Bianchi identity. And this Bianchi identity is equivalent, is nothing else as the first pair of Maxwell equations. So this is equivalent to these equations. Divergence of H is equal to 0, and dH over dt is minus C curl of E. Yeah, so this is the same as Bianchi identities. And the Bianchi identity, it straightforwardly follows from the definition of f mu. If you substitute here the definition of f mu, plug in, differentiate, and you will see that all the terms cancel. And you will get this Bianchi identity, and this is the first pair of Maxwell equations. Now, in the absence of sources, equations of motion, so this means the second pair of Maxwell equations has the following form. So let's write equations of motion. So second pair. So this is the first pair. And second pair. It looks like this. d mu f mu is equal to 0. Would there be sources in the presence of sources, then it would look like d mu f mu, and then on the right hand side there would be a current, source current, J nu source. Okay, so that is the second pair of Maxwell equations. So Bianchi identity together with dynamical equations d mu f mu is equal to 0. These are all system of Maxwell equations written in a covariant form, Lorentz covariant form. Yep.
This equation of motion for second pair also follows from the Coulomb gauge, right?
No. There is no gauge. No. There is no gauge. This is simply, this equation simply equivalent to the second pair. So that's, it includes both divergence of E is equal to 0, Gauss law, and also dE over dt is equal to C curl of H. No Coulomb, no. That has nothing to do with Coulomb. This is simply first and second pair of Maxwell equations written in the covariant form.
Okay.
Sir, does f mu nu here stand for Yang-Mills action?
No, Yang-Mills does not appear yet. Our field is just electromagnetic field, so describes electromagnetism.
Okay.
Our theory is abelian, so potential is abelian. There is no group structure. There is no Yang-Mills field here. Okay.
Okay.
In the case of Yang-Mills, you will have here. You need to use here covariant derivatives, which includes the mu, which includes the Young-Mills field. So far, it's just usual electromagnetism. So electricity, magnetism, and light. This is all together, which sits in this F mu. So E and H, electric and magnetic fields. Nothing more than that. Now, okay, so we understand that basically Bianchi identities, the first pair of Maxwell equations, simply automatically solved due to the introduction of electromagnetic potential, and the actual dynamical equations are these ones. And these equations you can obtain from the action. So action principle, where you consider action as a functional of electromagnetic potential of A mu, and it is given by the following formula: -1/4c integral d for x f mu, where over indices mu and nu there is a summation as usual, Einstein convention for summation of indices. So over f mu and nu you are summing up. Now if you put c to 1, then of course action takes this form. Now you can see that from this action you get this equation of motion. That's very easy to show if you vary S, so variational principle, get -1/4, 1/2, because you have twice f mu, d for x, and then say you apply delta, you write f mu as d mu a nu minus d nu a mu, f mu. So f mu is skew symmetric, therefore here these two terms give the same contribution with the opposite sign because it's skew symmetric. So you can write it as a minus twice d for x delta applied to d mu a nu, f mu. This is minus integral d for x d mu delta a nu, f mu. Then you integrate by parts. You get integral d for x delta a nu d mu f mu. And this must be equal to 0. So by basic lemma variational calculus, this can be only 0 for arbitrary delta a nu if this expression d mu f mu is equal to 0. And this is exactly the equation of motion which we have discussed. So this action f mu, this is the action of electrodynamics. This is what gives without sources for the moment, but this is what leads to equations of motion, second pair of Maxwell equations. Now, integrating by parts, you can always you can also bring this action to the form S on A mu is equal to 1/2c integral d for x A mu, and then here in the brackets you will get the following expression: eta mu nu d rho minus d mu d nu a nu. So the point which I would like now to discuss is the following. Because the action depends on f mu, and then the f mu is immune to gauge symmetry. So in other words, it does not change under symmetry transformations, under this gauge symmetry transformations, as we discussed. This action is invariant with respect to the gauge symmetry, with respect to the local symmetry. So invariant under gauge transformations. And that's, of course, brings trouble for instance, with the definition of the propagator. Because the propagator, as we just discussed an hour ago, is an operator inverse to the quadratic, to the one which defines the quadratic part of the Lagrangian. And we see that operator which defines the quadratic part of the Lagrangian is an operator given by eta mu d rho minus d mu d nu. Right? This is what we have. But this operator is not invertible. This operator is not invertible because this operator has a kernel. This operator has a kernel. What is a kernel? So kernel is a function such that if you act with this, actually this it can be vector, such that if this operator act on it, the result is 0. And so what is a kernel? Kernel is exactly the gauge transformation. So if I
I'm
act,
sorry.
yeah.
Why do we suddenly start caring about this if before we used like the inverse of the Laplace operator, which is not invertible either?
No, Laplace operator is
So
invertible.
why can't we just use Green's function again?
Yeah, because this operator has a kernel.
But Laplace operator also has kernel. All harmonic functions are in the kernel of the Laplace operator.
Yes, but when you consider the whole space, when you consider you don't consider operator, you don't consider solution in the finite space. You consider it in the infinite space, not in the finite space, but in the infinite space. The solution which I have written down with the help of the Green's function is solution which is a solution written in the infinite space without, in other words, there are no boundaries. Boundaries where you can consider.
You mean that we live in the Schwarz class and therefore all solutions must be 0 at infinity?
Yes, we impose the condition that our solutions are 0 at infinity. All fields must vanish at infinity. That's the condition we impose. We look for a solution in the whole space with a condition that all our fields vanish at infinity, indeed. That is our requirement. But here situation is, and in the case of the, say, Dirac field or Klein-Gordon field, there is no gauge symmetry. There are no transformations which I can do, transformations which are space-time dependent. There is no possibility to perform such transformation. There is simply no such a symmetry. In this case of electromagnetic field, as soon as you work with electromagnetic potential, there is such a symmetry, and this symmetry lies precisely in the kernel of the operator, which defines the quadratic part of the Lagrangian. And you see it immediately. If you take d nu chi and act on it with this operator, you see exactly what happens. You get d mu d rho acting on chi, that's the first term, and then minus d mu sorry, d mu here with low index, of course. D mu d rho sum over rho here, minus, and here you see nu, it's like d nu, it's the same as d rho is 0. So this is kernel. So gauge transformation, well, this gauge addition, gauge, gauge transformation is precisely in the kernel of this operator for arbitrary chi. So this means that the situation looks as follows. In fact, you have, say, all possible AMU configurations. Let's denote them by this list of all possible AMUs. And then you start from some AMU, and then through this AMU, you can draw an orbit, which is an orbit of all gauge equivalent configurations which you can obtain from a given one. So a mu given plus d mu chi for all possible chi's. It gives an orbit in the space of all AMUs. Then you pick up another AMU which is not on this orbit. And through it, you also can draw an orbit, and another orbit, and another orbit, and another orbit. And so this means that the whole space of all possible AMU configurations is foliated by the gauge orbits. As people say, foliated by gauge orbits. And all possible potentials, electromagnetic potentials, which lie on the one and the same orbit, live to the one and the same physics, because for all the points on this orbit, the values of E and H are the one and the same. So all states belonging to the same orbit describe the same physics and correspond to the same physical state. Therefore, idea in general consists of treating such a theory consists in picking up from each orbit just one representative. It is enough from each orbit to pick up just one representative. And that's already enough to describe physics. Say from here, we take one here, one here, one here, one here, one here. In other words, if you consider this situation, in continuous setting, it looks like all what you need is to draw a curve which, in a sense, pick up only one representative from each orbit. And this is exactly what corresponds imposition of the gauge condition. And of course, you understand that gauge imposition, that gauge condition will be imposed in a good way, in a proper way, if, of course, you don't have a situation like, for instance, this goes back and so intersects, say, one orbit twice. This would be bad. This would be a bad imposition, because, yeah, you see, you will not pick up just one representative, but you will pick up two, and so on. So that's exactly what you need to do. By the way, I forgot to mention, it comes to my mind now, when I was discussing imposition of the Coulomb gauge, I forgot to mention that once you impose the Coulomb gauge, the potential A0 is automatically zero because of this formula. You probably noticed this, but I forgot to mention it. Yeah, you see, A0, we solved for it, but the right-hand side is proportional to divergence of A. So once we said that we impose Coulomb gauge, then this vanishes, and therefore A0 vanishes. And so this shows that actually, with an imposition of the Coulomb gauge, you remove 2 degrees of freedom. You remove A0, and you have one more degree of freedom, which goes because of this condition, delta A, delta A is equal to 0. And so that explains why physical photon as a free state has 2 polarizations, 2 degrees of freedom. You see, one goes because A0, and another goes because of the Coulomb gauge. So photon has 2 physical degrees of freedom. And this is an argument showing that this is the case. Okay, what else? So basically, my discussion here shows one thing, that you cannot define in quantum theory the Feynman propagator for electromagnetic field without fixing the gauge. That is a moral out of this discussion, if you wish. Let me now discuss probably the origin of the Coulomb law. So Coulomb law, we all know what is this. But let's see how we can describe it mathematically. How do we see mathematically the appearance of Coulomb law? Let's write the full action of classical electrodynamics. Classical electrodynamics for the moment. Quantum electrodynamics is a little bit different thing, because quantum electrodynamics takes into account spin of electrons and positrons. Classical electrodynamics do not see spin. It sees charge, but it does not see spin. And so the action, full action of classical electrodynamics has the following structure: full action. Now, also in the presence of particles, in other words, sources. Let me do black. Okay. So the action looks as follows: full action of classical electrodynamics. How it looks like. S equals. First, there is an action for free particles, like electrons, positrons, or whatever particles. For particles, the only Lorentz invariant action is something which can be written via 4 interval. So 4 interval is the only Lorentz invariant quantity which you can associate with a free particle, and the corresponding action describing particles looks like this: minus mc integral ds, where ds is a 4 interval. And you know what is a 4 interval? 4 interval, the ds squared is x 1 minus x2 differential. Okay, let's write it in a differential way. So this is simply then, if you write it in a differential way, dx0 squared minus dx1 squared minus dx2 squared minus dx3 squared. Is it familiar to you for interval?
Yes.
Okay, very good. So the integral of ds over the world line of a particle, then this is how the action for a particle looks like. Then we have action for electromagnetic field, which we have discussed. So minus 1 over c integral f mu d for x. And then, so we have particles, we have electromagnetic field, and now we have to add a term which describes coupling of electromagnetic field to particles. And this is given by the following expression, which is also Lorentz invariant. 1 over c squared integral a mu j mu d for x, where j mu is a 4 current. J mu is a 4 current, and it includes, J mu includes it's a particle density rho and 3 current, which I denote as a G with vector, particle current. So this is a source for Maxwell equations. Source for Maxwell equations. So this is the full action of classical electrodynamics. This is how it looks like. Particles, fields, electromagnetic field, and the coupling between particles and electromagnetic field.
What is the first term here?
What is so?
The first term here in the action minus m integral of ds.
ds, yes. So this ds is an interval, is a full interval. In front of this is minus mc, mass multiplied by speed of light.
Okay.
Which makes this action to have a dimension of h bar. Because ds has dimension of length, mc is momentum, so momentum by length is h bar.
So total here, total our Lagrangian here is spatial part plus electromagnetic part, right?
Yeah, Lagrangian would be, in this case, would be mc ds plus f mu plus g mu j nu. Right. But you have to be careful. I mean, this is integral for integral. It's taken over the whole space, for space. Here is also over for space, but here integral is taken along world line. So world line in the for space, and you take interval ds and you integrate it. So it gives you a length in the four-dimensional world. Length of a world line, in a sense. So it's a complicated object. If you consider this action altogether, this is a complicated thing. Now, this action allows to derive the force between two static charges. Static means that these charges are, how to say, they are kept at the one and the same position. They are not allowed to move, so they are static. And one measures the force which arises between these two static charges, and this force between two static charges is exactly what we call Coulomb law. And to derive the force, I will assume that gauge field is present in the form of a static. In other words, time-independent scalar potential. So I assume that there is only scalar potential. We denote it by A0 and the same as phi. And there is no scalar potential. There is no vector potential, and everything is static. So scalar potential, this A0, I assume that it's created by an unvanishing charge density J0. So J0 is the same as this rho, which I'm writing here. So it's a zero component of J mu. So let's assume that A0 is created by G0. So in other words, I have Maxwell equations. D mu F mu, D mu F0 is equal to J0. So J0 is a source, and the potential, electromagnetic potential, which defines this F mu 0 is response A mu. So if you write this equation explicitly, then this is nabla to A0 plus 1 over C dA over dt, nabla A is equal to minus J0. And in fact, since we don't have magnetic field, this is absent. You get Laplacian, again, in the whole space with vanishing boundary condition at infinity. You solve for it, and you get an answer. dy G0, it's a green function again, on y, 4 pi modulus x minus y. And this is potential depending on x. So this is how potential looks like. And therefore, the energy, and this is this coupling between A mu and J mu, potential energy between two static sources is integral dx G0, let's say G01 on x, acting on A0, and then let me write here probably for this 0, let me write here 2, because it's a second source. It's a source which produces A0, and then this A0 couples to the source, to the first charge, with a density G01. And so when you substitute it in there, you will get what you will get. You will get integral dx dy G10 x G02 y divided by 4 pi modulus x minus y. And this exactly what you see here, what you read here, is a potential between two static sources. So if you take the source in the form of point-like source, so like Q multiplied by, so Q is dimensionless quantity, and say we multiply it by square root of h bar c, which has dimension of electric charge, and then delta function, say x minus x0, and then the same is for y. Plug it in, integrate, we get the following answer. For the potential, it will give us 1 over 4 pi q squared h bar c, because it comes from two sources, divided by r, where r is the distance, it comes from this term, the distance between these two charges, which is of course the same as 1 over 4 pi e squared divided by r, and this is Coulomb law. So essentially, Coulomb law comes due to this interaction term in the Lagrangian. So potential is positive, as you see, which means that equal charges repel. It means it's positive, so in order to decrease the potential energy, the distance between the charges must increase. So R must be bigger and bigger than V will be smaller and smaller, which exactly means the charges repel. They have a tendency to separate. And as we know, this is quite opposite to the Klein-Gordon field. In the Klein-Gordon field, equal charges attract. And this fundamental difference with the case of Klein-Gordon field, you can trace it back to the fact that for the later case, field phi enters into the action in the form, in the following form: S is 1 over c integral dx di phi di phi. While the scalar potential A0 responsible for this Coulomb interaction enters in the action in an opposite way with the minus sign, minus 1 over 4c. If you trace it to the action, then this is dA0, dA0. So it comes with a minus sign, and this is fundamental difference between these two cases. Okay.
Professor,
Yes.
I remember when we performed a similar calculation in the Yukawa theory.
Yes, exactly. Absolutely. Yeah, it's the same calculation I'm doing here.
Yes,
it's the same.
But I remember that you, maybe I'm wrong, but you use the propagator to take into account the propagation of the interaction.
This is the same thing. The same thing. This is a propagator. This is a propagator which I'm using. This is a Green's function, exactly. This is a propagator. I'm doing now. It's a bit faster and simpler than I did that time. This is a propagator, exactly. So you have a source, and this propagator propagates an interaction in the form of the scalar potentials. So scalar potential mediates interaction between these two sources. So one source, J02, produce J02, produce scalar field. Scalar field propagates and interact with the second source. And so they start to talk to each other due to the scalar potential. And this is a force, this is a potential which arises. And this is Coulomb law. Now, you may ask why I do not change sign in front of Lagrangian for electromagnetic field in order to get opposite effect, right? You may ask this question, why I'm putting here minus instead of plus. If we put here plus, then the energy of the electromagnetic field come out negative, which is, of course, not allowed, prohibited. You want energy of electromagnetic field obtained from this action to be positive. And that requires minus sign in front of this Lagrangian. And that, as a result, leads to the appearance of the field A0, which mediates interaction in the Coulomb case in this way, as I'm writing here. And as a result, you get Coulomb law. That is an explanation. Okay, I think my time is up. For today, we did a lot of work. We considered quantization of Dirac field. We considered classical electrodynamics. And what I'm going to do next time, I will present you the Hamiltonian formulation of electrodynamics and perform quantization of electromagnetic field in the Coulomb gauge. That is the plan for the next lecture on next Friday. Two lectures next Friday. Okay, with this I finish. If you have questions, please ask.
Yes, sir. Sir, can you explain that again, that imposition of the gauge condition? Sorry, I missed that part.
Yeah. So once again, if we consider the space of all possible configurations A mu, then we can split the whole space into orbits of the gauge transformation. So we start from some field A mu, and then we consider all possible fields which we can obtain by adding to A mu a gradient of arbitrary function. That makes from this A mu the whole orbit passing through this configuration. But that, of course, does not cover the whole space of A mu. We may start from another A mu, which is not on the orbit, and take another orbit, and so on. And so in this way, the space of A mu's, of all possible A mu's, is divided by orbits into classes, into, if you wish, equivalent classes. So we partition the space of all A mu's into classes of gauge equivalent configurations. No, people say sometimes that we foliate the space of all A mu's by gauge orbits. And then if you want to describe physics, it's enough to pick up at each gauge orbit just one representative, one configuration A mu. Because any other configuration on the same orbit leads to the same physics. You don't need to account the same thing several times. And so you pick up from each orbit one representative, only one representative, like I'm describing here. Like one representative from each orbit, you pick up just one representative. But in reality, what it means that you need to impose a condition which pick up from each orbit one representative. And for instance, what this line which I'm drawing here as red is exactly the imposition of the gauge condition, which in a way a curve in the space of A mu, which is in a sense orthogonal to the gauge orbit. It's not necessarily orthogonal in a strict sense of the word, but it's a condition which picks up from each gauge orbit one representative. So in our case, this is Coulomb gauge. Divergence of A is equal to 0. This extra condition allows me to pick from each gauge orbit one representative. That means that if I do gauge transformation on this Coulomb gauge conditions and I destroy it. There are no gauge transformations which preserve this condition, divergence of A is equal to 0. Gauge transformation destroys it. I get out of the gauge. And so that means that as soon as I impose this condition, gauge transformation are gone. I cannot perform them anymore. They are gone, I fix the gauge, and that's what makes theory sort of well-defined in a sense that I will be able to find propagator and so on. Okay, so this is an idea.
Okay, yes.
Something, you need a condition which is transverse to the gauge orbit in some sense of the word. Pickups one representative from each gauge orbit.
Yes, understood.
Mm-hmm.
Another question, sir, that at the last point you mentioned that the reason why we didn't put minus sign in the scalar
Yes.
field theory is because that phi the scalar field attract each other, right?
Mm-hmm.
So
Yeah,
it means if I think about it, so is that a reason why we get mass? We say that boson, right? Higgs boson something to that phi.
why we don't have mass? Mass breaks gauge invariance. Mass we cannot add because mass for electromagnetic field will destroy gauge invariance. No, and also we know, of course, that light is massless in the sense that there is no rest mass.
No,
If you're talking about this, or maybe you're talking about something else.
No, in scalar field theory. So in scalar field theory, the Klein-Gordon equation, scalar field is supposed to be Higgs boson, right?
Higgs boson could be considered, yes, it's a scalar field, yes.
Yes, so means here they attract each other. So is this a reason why Higgs boson creates mass in every particle?
That's because of the spontaneous symmetry breaking mechanism. That is a bit different story. You need to give a vacuum expectation value for the field, and this vacuum expectation value leads to the appearance, it gives rise to the mass, and the phenomenon, the mechanism which is responsible for that is a spontaneous symmetry breaking mechanism. I don't know, maybe we at a certain point come to the discussion of this.
Okay. Get it.
Spontaneous symmetry breaking, these are crucial words which are responsible eventually for this for this phenomenon, so to speak.
So these particles self-interact attractively.
Yeah, so there is an electromagnetic field, and in simplest way, you can explain Higgs phenomenon by considering boson. By considering scalar field interacting with electromagnetic field. And eventually, if you give to the field phi vacuum expectation value, then this will lead to the appearance of the massive mode for electromagnetic field. So it's actually one of the modes becomes massive. In that case, due to the fact that there is this vacuum expectation value for the field A, for the field phi.
Yes.
Okay. So if you don't have any questions, then I wish you a pleasant day, and we see and hear each other next Friday.